Young's modulus. What is Young's modulus? For an object that is subjected to a tensile stress, there will be a tensile strain. Is that right? If you now take the ratio of the tensile strain, the tensile stress to the tensile strain, that ratio is called the Young's modulus of that material. So the ratio of tensile stress to tensile strain is called the Young's modulus of elasticity. It's the modulus of elasticity. So what is the definition of Young's modulus? Young's modulus is the ratio of tensile stress to tensile strain. You can see if you have a big column in here, and if you apply a force F on it, that will cause a decrease in length, a change in length to delta L. That delta L divided by the original length will be the tensile strain. And what is the tensile stress? Tensile stress is this force F is applied on this area A. So the tensile stress will be that force divided by that area. So stress is force divided by the area. The strain is delta L divided by L. And Young's modulus is the ratio of stress to strain. In other words, stress divided by strain is a measure of the Young's modulus of the material of this. Now, we represent the Young's modulus by the letter Y. If Y is the Young's modulus, what is the equation for it? It is tensile stress divided by tensile strain. And in this case, the tensile stress is F divided by A. A is the area which I am now pointing. That is the area on which the force is acting. So the stress is that force divided by that area, and the strain is delta L divided by the original length. So I can write it as F over A divided by delta L over L, and that is the Young's modulus of elasticity. What is the unit for measuring Young's modulus? You know that the unit for stress is Newton per meter square. Unit for strain has no unit. It is a ratio of two similar quantities. Therefore, the unit of Young's modulus is Newton per meter square. Let's solve this equation for delta L. Can you do that? You have a Y equal to, let me write that over here. Young's modulus Y equal to F over A divided by delta L divided by L. Now, this is stress divided by strain, and that will be F times L over A times delta L. Is that right? F over A divided by delta L over L. This L will go up. F times L over A times delta L. Can you solve for delta L from here? Well, delta L, if you cross multiply, Y times A delta L equal to F times L. So delta L will be F times L divided by AY. Is that right? Okay, let's write that down. So delta L is F times L over A times 1 over Y. That is the change in length under this stress. So the increase in length of a rod or wire under tensile stress is inversely proportional to to the Young's modulus of the material. That means greater the Young's modulus, less will be the deformation. So if you want to use a material for hard construction, you need a material of very large Y value, a very large Young's modulus, so that under the action of great stress, the deformation will be very, very small. Okay, let's now talk about bulk modulus. Bulk modulus. Well, I think it follows from our discussions. Bulk modulus is the elastic modulus that talks about the change in volume. The ratio of the volume stress or the bulk stress to the volume strain is called the bulk modulus. Now we normally represent the bulk modulus by the letter B. So B equal to volume stress divided by volume strain. And volume stress is, of course, F divided by A. And volume strain is the change in volume divided by the original volume. And can you solve for delta V from here? Well, again you can see B is measured in Newton per meter square, which is the same as the unit for measuring stress. Well, the reciprocal of the bulk modulus, the quantity 1 over B, is called the compressibility of the material. How easy is an object, how easily can you compress an object? The value, the compressibility of a material tells you how easily it can be compressed. And that is the reciprocal of the bulk modulus. What does that mean? It means greater the bulk modulus, greater will be the difficulty to compress it. In other words, 1 over B, when B is very large, 1 over B is very small. The compressibility will be very small. For an object of very large bulk modulus, the compressibility will be very small. It will be very difficult to compress it. So 1 over B is called the compressibility of the material, and we represent it by the lowercase k. K equal to 1 over B. Let's now talk about the shear modulus. Shear modulus. Now we talked about the shear stress. Shear stress is caused by parallel forces which changes the shape of the object at an angle. And what is the shear strain? Well, let's talk about that. The shear stress is produced when a force is applied tangentially to the surface, like this. You have the original surface, apply a force tangential to that. This is a shear force, and this creates a shear stress. Tell me, if this force is acting on this area A, what is the shear stress? The shear stress is F over A. Now what is the shear strain? You notice that the strain in this case is actually measured in terms of the angular deformation. The deformation here is measured in terms of the angle. Therefore, the shear strain is the tangent of the angle of deformation. So here the change in shape produced by the stress does not involve in a change in volume or change in length, but involves in a relative displacement of two surfaces of the body. You see, the lower surface has not moved, but the upper surface has been displaced. A relative displacement has occurred for the two surfaces. That means the deformation is actually an angle. the shear strain is given by the tangent of the angle of deformation. Now, this angle is the angle of deformation, and that will be, therefore, the tangent of that angle will be the shear strain. Now, if this is the angle here, tell me what is the tangent? If the upper surface has been displaced by a quantity delta L, that means this length is delta L, and the height of the object is h, has the height changed? No, the height hasn't changed. So, if the upper surface has been displaced by a small distance delta L, then the tangent of the angle of deformation will be that opposite side divided by the adjacent side. Delta L divided by h is the shear strain here. So, shear strain is tangent of the angle of deformation, which is delta L divided by h. Okay. We represent the shear stress by S. S represents the shear modulus of the material, not the shear stress, shear modulus. So, shear modulus equal to shear stress divided by the shear strain. And what is the shear stress in this case? It will be F divided by A, and the shear strain is the tangent of the angle of deformation, which is delta L divided by H. So that will be S, the shear modulus, is F over A divided by delta L divided by H. Now, shear modulus may also be a torsional type, resulting in the twisting action. A torsional type. Now, what is that? What is a torsional type of deformation? Let me see if I can show the torsional type. Now, if this mass is hanging from this wire, look at what happens when I twist this mass. When I twist this mass, what it does is it is turning this wire. It is turning this wire. In other words, this shear modulus is kind of torsional modulus. You see, the change in angle is actually producing a change in angle, twisting of the wire. Now, it is fixed where I'm holding. That means the wire is now being twisted, or the shear strain is the angle of twist. So, the shear modulus may also be a torsional type, resulting in the twisting action of a torque. Now, you understand what that means. Alright. I have now got a table of values that shows the standard values of the Young's modulus Y, the bulk modulus B, and the shear modulus F of some common materials. If you are a civil engineer building bridges and constructing big buildings and so on, you should be familiar with these properties of the materials. Is that right? Now, here is the table of values. You got the material aluminum. The Young's modulus is 7 times 10 to the 10 Newton per meter squared. Its shear modulus is 2.4 times 10 to the 10 Newton per meter squared, and its bulk modulus is 7 times 10 to the 10 Newton per meter squared. You can see the modulus of elasticity, all three types, are measured in Newton per meter squared, which is the unit of stress. The unit of strain, strain has no unit. Well, if you look at steel, Young's modulus is 20 times 10 to the power of 10. It is very highly elastic. The shear modulus is 8